Alright, so in this video what we'll be doing is taking an introductory look at scalars and vectors. This is part one of a mini-series on this topic or these topics. So where would you hear about scalars and vectors? Well, scalars and vectors are terms that you'll hear pretty often, for instance, in physics and engineering type classes or in those environments. What exactly are scalars and vectors? All right, so a scalar is a quantity represented by magnitude only. And typically we label a scalar by using some lowercase letter in order to represent the scalar. Some examples of scalars, well, we have length, temperature, speed, and resistance. A vector, on the other hand, is a quantity represented by magnitude and direction. And to label those vectors, typically what we use is some capital letter that is not italicized or bolded. We may also find in certain books they reference or talk about vectors or label vectors as lowercase letters that have been bolded, or sometimes you'll see a lowercase letter with a half arrow, if you will, above the letter to indicate that it's a vector. Okay, some examples of vectors in physics and engineering. Well, you have displacement, velocity, force, and electric field. Now, as I said, there are many others, but these are just the ones that I wanted to present at this time. Of course, you can look into different books and so forth and see other examples. Okay, so now that we've talked about what exactly a vector is and what exactly a scalar is, now let's look at more at vectors. Vectors can be represented in two different ways or two different forms. We have the polar form and we have the rectangular form. In the polar form, the vector is represented by the magnitude. We'll use the letter R to represent the magnitude, and we use the Greek letter theta to represent the direction. If we combine them together with the R angle theta, that will be equal to, we'll say, Z for now. And so when we're looking at the vector represented in polar form, it is written as some magnitude angle theta. Okay? Now, in rectangular form, the vector is represented as, or what exactly is it? It's a projection of the vector on the x and y axes of a rectangular coordinate system. Okay, and we'll talk about exactly what that means just a little bit later. So in this case, you have some x value plus some y value, and those two together are equal to z. Okay, now let's start off by looking at vectors in polar form. So graphically, vectors are illustrated by some arrow, where the arrow begins, we call the origin. In this case, I represent origin with the letter O. And where the arrow ends, or the vector ends, same thing, you can say that's the point at which it ends, and I indicate that by using the letter P. Now, the length of the vector is, to scale, related to the actual magnitude of the vector quantity, okay? So it's related to the magnitude. That length of R is in scale with the actual magnitude or of the quantity that you're measuring or that the vector measures, okay? If the vector points to the right, directly to the right, then we say this vector has a direction equal to 0 degrees. Okay? Again, if it points directly to the right, we say it has a direction equal to 0 degrees. What if we had the vector pointing in different directions? Well, in total, we have 360 degrees if we were to go around in a full circle. So what this means then is if the vector starts from the origin, its origin, and points directly straight up, then we say that the angle is equal to 90 degrees. Okay, then the vector has an angle of 90 degrees, and that's pointing straight upward. Okay, what if the vector then points off to the left? So we start with the origin here and we move off to the left over here where we end at the point, the head of the vector. Then we say that this vector has an angle of 180 degrees. All right, let's say we have a case where the vector is pointing directly straight down. What do we say in terms of what is the angle of the vector? Well, in that case, then the vector has an angle of 270 degrees. And so that means we're starting from here and going all the way around to come to this point. Now, we can say it's 270 degrees, but we can also say that this is minus 90 degrees. And what that means is that we start from here and go back this direction. Okay, so if we go counterclockwise, we're going to be using plus degrees, and if we go clockwise in this case, then we'll say it's minus whatever degrees. Okay, and we have one more that I'd like to take a look at, and that's if the vector is back now to the original starting point, if you will. If it's pointing directly off to the right. We can also say that it's 360 degrees if that vector, we can say, went all the way around. Okay, so 360 degrees for theta is also at the same location, and therefore 360 degrees and 0 degrees ends up being the same thing when it comes to the vector. All right. All right. Now we may divide the 360 degrees into 4 quadrants. 4 even quadrants. So within this area here is the first 90 degrees. Within this area here is the second 90 degrees. Then we have third 90 degrees and fourth 90 degrees, totaling up to our 360 degrees. Now, remember, the origin is where the vector starts. So if we break this up into 4 different quadrants, then that origin we can say has a location of 0, 0. So what does that mean in terms of having the location of 0, 0? Well, what we're saying is that in terms of our position on the x-axis here, which is the line here that separates the upper half from the lower half, we're saying that that x-axis, the origin is at 0, and what we're saying is y here, or 0, the second 0 here, is the position on the y-axis, and that would be this axis here, and we're saying that its location is also 0. Okay, so now what you may have noticed at this point is that I have this plus plus here within these 2 parentheses. Okay, what this means is that everything within this quadrant, and we'll call this quadrant quadrant 1, everything within this quadrant will have a positive x value, and it will also have a positive y value. Okay, positive x and positive y. Everything within this quadrant here, and we'll call this quadrant 2, will have a negative value, and the reason it's negative is because remember the origin, which is the point where the vector starts, is at 0, 0, right? Since the origin is at 0, 0, then that means everything to the left then is going to have a negative value, and we'll say that's just the negative x-axis. So everything within quadrant number 2 will have a negative x, and because it's above this x-axis here, it will have a positive y. So everything in quadrant 2 has a negative x and a positive y. Down here in quadrant number 3, we have a negative x value and we have a negative y value. So everything in here has a negative x and negative y. Quadrant number 4 here now, in our last quadrant, everything in here has a positive x and it has a negative y. Positive x and negative y. So again, these values here, or not these values, but rather these signs represent what the actual value here for x would end up being. The value for x would end up being negative. Value for y in this case would end up being positive. Okay, now in some cases you may see where instead of saying x and y we use I and j. I for the x-axis and j for the y-axis. Okay, you may end up seeing that sometimes. All right, so let's move forward. Okay, let's say now we're looking at this in rectangular form. We just looked at this in polar form, right? Let's say we're looking at this in rectangular form. Remember, in rectangular form, we say that in rectangular form, the vector can be broken into x and y coordinates, okay, where it's a projection onto the x-axis and the projection onto the y-axis, okay? So if we were to lay down flat on the x-axis here and we look up, it would look like the vector is only this long, okay, which is not actually how long the vector is, but that's how long it looks from there. That's how long it projects onto the axis, okay? And we can say that that projection we'll just call a sub x, okay? Now, if we were to stand straight up here and look at the vector out there, that vector projects back to our eyes as if the vector is only this high. And so we can say that this is a projection on the y-axis, and we can call that a sub y. And this is for a vector, by the way, that we named A, okay? And again, you'll notice that the vector begins at its origin, which is right here, and it goes to this point here, okay, that we call P. And again, this vector here has some angle, and we'll just call that angle theta. All right, so if we want to write this as some sort of a mathematical expression for the rectangular form, we can say that A is equal to a sub x x plus a sub y y, okay, where this is just simply saying the value for x, meaning the value on the x of its projection on the x-axis, value of the vector as it projects onto the y-axis, and that, but those two together represent the vector A. And also, again, you can use I and J to represent the same two. Okay, sometimes you'll see it listed that way. All right, so what if we have the vector now over here in quadrant number 2? Well, you know the angle goes from here to here, okay? And again, the projection on the x-axis would be here. Projection on the y-axis would be here. And so we can say that this vector, again, is a sub x of x plus a sub y of y. All right. Or we can write it this way, where a sub x, by the way, since it's over here on the negative x side, this is going to have some negative x value or some negative value. Okay. All right. So this concludes our introductory look at scalars and vectors. This is part 1 again. Please do check back for part 2 of this mini series on my YouTube channel, or if you want additional information on just physics and engineering related stuff, you may also check my website. My website is at www.clydeletsam.com, and you can get additional information there as I stated. All right, thank you.